Hello and welcome to this SimScale webinar on increasing ventilation performance of HVAC units. My name is Dr. Nagman Khan. I'll be your moderator today and I'm delighted to be joined by my colleague Ajit, who's an application engineer here at SimScale. Welcome. What are SimScale doing? Well, firstly, we're empowering engineers to innovate faster. And we're doing this by making high-fidelity engineering simulation truly accessible from everywhere and at any scale. And why is that important for today's application? Well, engineers are trying to optimize the aerodynamic and pressure flow characteristics of ventilation equipment. And that's critical for enhancing the overall product performance. Now, we know that most types of ventilation equipment, they need to be designed to allow the maximum airflow through them, whilst reducing the pressure drop across the unit. And optimizing the blade or fin angle on a diffuser, for example, is an application where engineering simulation can assist manufacturers and suppliers of HVAC products, but also assist designers and engineers in sizing and placing ventilation equipment concisely and clearly and more accurately. Now, today's agenda, we're going to see how CFD analysis is used to optimize the airflow performance of ventilation products and HVAC units with engineering simulation in the cloud. We're going to have a live question answer session and demonstration on the SimScale platform. And at the end, we're going to show you how to get started with using SimScale. Let's first take a look at some applications where we simulate HVAC products using SimScale to give you an idea of the types of simulations and models that are possible. Well, first, let's take a quick look at air handling units. Very common application in most types of commercial, industrial, retail buildings. So SimScale CFD is used to simulate the airflow through air handling units, as you can see in these images. And some of the things you can calculate are flow rates, so how much air is flowing through a complete unit. Now, a complete unit, as you can see on the image on the bottom right-hand corner, might be made up of multiple screens, filters, dampers, louvers, grills, the ducting itself, and each one of those has a pressure drop across it. So when you put all of them together in one complete unit and then place it in the overall building ducting, what is the flow? How does it move? How much flow do you really get? This is important. Obviously, with flow rates, you calculate the pressure drop through all those individual components. You can look at the impact of angle-dependent pressure drop through dampers, through different types of louvers and grills. You can look at pressure drop across air filters. Very important now, this with everything that's been going on with COVID, supplying more fresh air to indoor spaces. And you can also look at vibration and structural stress. And once a CAD model is in, it's easy to change the model. So you can simulate various scenarios and configurations of that one model in SimScale. Ventilation louvers is a very common application. We can use SimScale and CFD to determine the nominal discharge coefficient of various products. This is important, for example, if you want to verify the performance of certain grills and louvers and other ventilation equipment. It's also important if you're trying to simulate for compliance and if you're using any kind of thermal modeling software. So the discharge coefficient is a quantity that describes the pressure flow characteristics of louvers and grills and various other ventilation equipment, and being able to model that properly and seeing what impact that flow distribution has inside a space is critical. And it's not something you can do with thermal energy modeling software because it doesn't model flow at a subzonal level, whereas CFD does. Now here you can see examples of the images on the right where we're optimizing the aerodynamic performance of louvers and grills. So again, you can model at a micro scale and understand the aerodynamics. You can look at things like stagnation, high velocity zones, separation points of the flow, wake regions, and where pressure loss occurs to optimize the fin or blade angle of the louvers themselves. And you can determine porosity factors, which are generic for any CFD tool for comparison purposes. Now here's an example where we took data from manufacturer's data of ventilation equipment. Typical data might include open area on the face. So if you look at a louver like this on the top right hand side, this had an open area of 67%, the louver angle was 17 degrees, and the open area in line with the louvers is 80%. So we can take this data and easily replicate the performance of this louver without necessarily having to model very fine geometric detail. And that's a great example of being able to do quick and early stage CFD simulation as well. Finally, let's take a look at different types of HVAC units and diffusers. We have customers using SimScale to design entire HVAC units and specialist diffuser grids. So on the top right, you can see a swirl diffuser, and it's been modeled in SimScale, and you can see the plan view in the top image and a section view in the middle image here. And this is really important. This type of diffuser is providing a swirl flow, and it's using something called the Coanda effect to distribute flow evenly inside a space. And all of these types of design and comparisons and analysis are possible in SimScale in our platform. And I'll hand over to my colleague Ajit to give you a live demonstration. Thank you.
Thanks, Nagman, for the brief overview of how simulation can actually support the design and development of HVAC systems. So in the next section, we'll be taking a look at two of the interesting cases using a live demo within SimScale, and I'll be talking about how you can set up these kind of simulations and get insights from them. So to start with, we'll divide the analysis into two stages. The first stage being the componential level analysis, where you can actually simulate your HVAC unit or your product to optimize or improve the performance of these particular units. And the next stage is the installation or a spatial level analysis, where you put this HVAC unit into a particular space and see how well it performs according to the space, so that you can also do a parametric study on how this unit should actually perform for a given space, whether if the space is a bigger space or a particular meeting room or an office room, and we can set the operating points according to that. Let's dive into the live demo and see how we can easily set up these kind of simulations and get insights from them. Before going on to the project, if you have any questions, please feel free to actually put your questions in the chat so that we can discuss it at the end of this session. Now we are inside SimScale. So for users who have not seen SimScale and are looking at SimScale for the first time, SimScale is a completely web-based simulation tool. As my colleague Nagman mentioned, you can simply open a browser, go to simscale.com, and then start simulating your required analysis or simulations. As we spoke about the first stage of the design analysis, where we take a HVAC component and want to see how well it actually performs, what are the insights that we can get so that we can use them for our design optimization. So here we have a air handling unit. So this unit basically consists of a blower at the front and with a series of heating elements and filters and some guiding vanes to actually guide the airflow from the ambient conditions. So here, once when the simulation is done, what you're looking at is the post-processing page of SimScale. Here you can extract the results, visualize them, and then get some insights about how well your unit actually performs. For example, let's take a look at a cutting plane at the midsection of this particular unit. And here I have plotted the pressure values at this cutting plane. So what you can basically see here is the pressure drop across the system. And if you're really focusing on one particular stage of this unit, let's say what's happening after this particular guiding vanes or the blades, then you can simply use this inspect point option to see the pressure across these particular sections. So you can click anywhere in the domain to see what is the pressure before and after this particular set of blades that you have here. On the visual side, you can also see the entire pressure drop across the system. And if you're really interested in one particular cross-sectional area, you can simply make a cutting plane at a different location or a different angle. For example, we want to see what is the pressure drop across this particular cross-section. Then you can place the cutting plane here, switch on the statistics where you can get the minimum, average and maximum pressure at this particular point. This is just not limited to the pressure variations, but you can also plot the velocity magnitude at this particular cutting plane, which will give you the flow rate across this particular cross section. You can also move around this cross section and then find out what is the flow rate or the pressure drop at different locations here. One other powerful visualization that you can perform is putting the streamlines. So the streamlines basically will tell you how the air actually moves in a 3D domain, and this will give you insight about whether we have a dead zone or a recirculation zone or anything that actually contributes to the pressure of the system. And now we have loaded a few particle traces here, and you can already see there's a bit of recirculation zone happening at the mid stage of this air handling unit. Let me also add one other particle trace at the beginning of the system. Let's play with few parameters, expand the number of seats so that we get a better visualization. And now what you can also do is animate the streamlines to see how the air actually moves through the system. To do this, you can press on the animation, click on the play button. This might take a few seconds to load, but once when it is loaded, you can already see how the air actually moves from the inlet and how the blower collects the air after these set of heating elements or filters pushes it out to the outlet. As the particle traces load, the key advantages of having all this simulation on cloud is not just limited to the access to the high performance computers. For example, you can run complex simulations with a large number of cores that doesn't affect your local hardware, or it doesn't actually strain the hardware so that you don't have to actually let the simulation run and wait for it to complete. So you can start a simulation and then start working on any other projects. So it's just not limited to this high performance computing, but you're also constantly being connected with our support team. So we have a bunch of experts from our team who are constantly online for the guidance. So for example, if you have any question on setting up this simulation, so if you're setting up a simulation, you don't know how to set the boundary conditions, you don't know how to visualize the results, then you can simply click the chat button at the bottom right corner of your screen, where you can send us a message and have a one-to-one conversation on your specific questions. So you type a question, send it to us, we'll answer it specifically for you. And in case if you want to actually show what you're simulating to actually gain insights on best practice guidelines, you can also share your project with our support. We can take a look at your simulation settings and guide you through the simulation settings. All right. Now that the particle traces are loaded, you can already see how the air actually moves from the initial stage to the end of this air handling unit. By taking a deeper look at the first stage, where the blades are actually positioned to streamline the flow, there is a bit of recirculation happening already at the bottom level of this stage. So you can focus on this particular stage try to optimize it by changing the blade angles or even changing the shape of the blades to actually improve the flow quality here. This can be also done at different stages. So you can see at the mid section where we have a heating element and a filter system, there is a bit of recirculation happening here, and a dead zone is happening due to the position of this filtering and the heating elements. So you can again focus on this particular level, try to optimize that so that you have a complete optimization of your unit or your product. Now that we have seen the results and the insights that we can get from the simulation, let's take a look at how we can set these simulations up. So we start from the scratch. So the first thing is to import your geometry. We do support a lot of native formats from SolidWorks, Autodesk Inventor, Rhino, CATIA, Creo, etc. and also general formats like STEP, IGES, STL, etc. So you drag and drop your geometry here, and once when your geometry is available inside SimScale, you can go ahead and create a simulation. When you press on create simulation, you find the different analysis type that is supported by SimScale, and you select the optimal or your required analysis type. So for this particular case, we are interested in both the fluid flow and also the heat transfer, because we have a heating element in this air handling unit. So we go for convective heat transfer and create the simulation. So now you have a simulation tree on the left side where you have to basically do a top-down approach on setting up the materials, the physics for the simulation, and then start the simulation. But in case if you're very new to CFD or any other simulation tool, you can also use what we have as a template. So for example, we can share you this project, and then you already have this particular setting as a reference for your next simulation. So you can simply go ahead and duplicate this setting. You'll get an exact copy of what we did in the first case, and now you can start playing with the parametric study. So for example, if you want to see how the blower performs at different operating points, you can simply go ahead, change one particular parameter and start a next run. So for example, instead of 10 meter per second, you want to check it at 12 meter per second. So simply change this one, start a run. So as I mentioned, the simulation setting is also easy. You start with the geometry, you select the materials that you are simulating, you put the boundary conditions. So for this case, there's going to be an open condition at the inlet at 35 degrees Celsius, ambient temperature, and an open condition at the outlet at 21 degrees Celsius. And apart from this, we do have two filters which are modeled using the perforated plate or the porous media. And we have a heating element which has a particular power value, or a cooling element which has a particular negative value, which is set to one of the volumes that you have modeled. And we have taken a look at how the blower can be set at different operating points. So once when these parameters are set, you can again start a simulation. So you can even start multiple simulations parallelly. So in case if you want to change the ambient temperature at the inlet, you can go ahead and change this particular parameter and then start a new simulation, so that all the simulations are running in parallel. By the end of a particular time, you will get the results for all the simulation. This is how we can set up a componential level simulation within SimScale. If you have any questions, I just gave a brief overview of how the setup looks like, but if you have a specific question on how to set a particular parameter or settings, please feel free to ask your questions in the chat box, and we'll be happy to answer at the end of the session. Now, moving away from the componential design, we want to see how this component actually performs in a spatial level, or when it is actually installed in a particular room or a space. So for this example, as we mentioned again, we'll be taking a look at a swirl diffuser. So how does this swirl diffuser spreads the air throughout this particular room that we have considered? Let's take a look at how the swirl diffuser looks like. So we have certain blades at particular angles so that the inlet air from the HVAC system actually gets spread all through the room. And we want to see how the air actually recirculates and gets out of the outlet here. So now, once again, you can put a cutting plane at any point in the domain to see. So I have put a cutting plane at the ceiling level right next to this swirl diffuser to see how the diffuser actually gives out the air. So you can already see the air is moving at a tangential direction all through the all around the swirl diffuser. This will already give you a brief idea of how the air is gonna move around this particular space. One other powerful tool that you can use is again the particle trace, where you can put the particle trace at the inlet and see how the air moves through the room. Let's put it at a particular view and animate this one. So now we can already see how the air comes in from the HVAC inlet, goes through the swirl diffuser, and then spreads through the room. So this way you can find out whether the diffuser is performing well, whether the air is actually moving across all the corners of the room, or if there is a dead zone at a particular part of the room which needs to be addressed for getting fresh air all through the room. Perfect. Now we have seen what you can do on a componency level and on a spatial level. So the simulation settings for even the spatial level simulation is similar to what we have seen in the previous setup. So you have the geometry, you have the simulation. So you model the material, give the inlets and outlets of the HVAC system, and then start the simulation. So in case if you have questions, once again, please post your questions on the chat box. We'll be discussing in the next couple of minutes.
Ajit, thanks so much for the fantastic demonstration in the SimScale platform. Let's take a few questions. We've had questions coming in. Thank you, everyone. Please keep posting more questions. Ajit, the first question was a more generic question about the kind of CAD formats which you can import into SimScale from different third-party CAD programs. Perhaps you can just elaborate on that.
Sure, thanks, Angwan, for the question. So within SimScale, we do support a variety of native formats from SolidWorks, Autodesk Inventor, Rhino, as I already mentioned in the presentation. So you can simply drag and drop your SolidWorks part file or even the assembly file, but we do also support a lot of general formats. So in case if your native format is not supported, you can simply write it out as a step format or an IGES format or a Parasolid format. So these are some of the few general formats we do support while importing.
Thank you. Thank you, Ajit. Well, let's take some more questions. So how about, so someone's asked about the demo project. So what we are going to do is we will share the demo project with you. Or give us a day or two and we're going to share the presentation with you as well, and the video recording of this webinar. And in the follow-up email, we can include links to some additional resources and these demo projects you've seen, so you can jump in and have a go yourself. Okay, let me take a couple of other questions. A generic question again, Ajit. What benefits does SimScale give me over using OpenFOAM? Maybe some high-level answers there, Ajit.
Sure, that's an interesting question because as you know, the physics behind the solver is the same. What we have done within SimScale is that we have taken all the pain and also the struggle that we need to set up a simulation in OpenFOAM. So you can already see our simulation setup is pretty much easy. So we mainly focused on the ease of use. You can simply click buttons and then start your simulation. And also we combine that with the power of the cloud computing. So whenever you start a solution, you can actually select the number of processes that you want to use. So in this case, you can actually go up to 96 cores of processors for each simulation that you start in parallel. So this is mainly the advantage of SimScale over OpenFOAM, and we also invested quite a lot in the meshing strategy or the algorithm behind this meshing. So when you take a meshing, we do have certain set of default algorithms which are running, which makes our users easy to actually refine only based on the fineness. You don't need to go for additional refinements. You can already see by keeping the default settings, all the features or the parameters here on the geometry are meshed accordingly. So these are some of the advantages that you have, but there's quite a lot we can talk about. Maybe we can set up a meeting and then let you know like the other differentiators that we project on SimScale.
Thank you, Ajit. And likewise to everyone else, if you have a particular project in mind that you'd like to discuss and see how SimScale can help accelerate your design and development work, please get in touch directly. We'll share the contact details shortly with you. Obviously, another advantage is you can just access SimScale through your web browser, through your preferred web browser. So you just need a simple username and login. You don't need to spend ages downloading and installing, native OpenFOAM and desktop software. So let's move on, Ajit. Thank you for that. Another attendee is asking if you can use SimScale for the simulation of water pipes. So simulating fluid flow through water pipes.
Mm-hmm. Sure. I mean, we do support a variety of analysis types. So for anything related to water pipe or air or any other fluid, you can simply choose the analysis type. So for example, you can go for incompressible and then import your model with a water pipe, and the simulation setup is going to be same. You have a velocity inlet, pressure outlet. You can calculate the pressure drops on any sort of fluid analysis.
Excellent. Fantastic. We have another question from Min, which I will probably have a crack at. So you're asking Min about AHU energy saving and comparing pressure drop across different filters and components. Yes, we can do that. If you have a specific project in mind, please do get in touch with us at sales@simscale.com, and we can set up a bespoke demo for anyone on this call who has particular problems to talk through. So let's take some more questions, Ajit. Another question here was about some of the elements we saw in the AHU. So how are filters and other elements actually modeled from a flow pressure loss perspective? That's a great question.
Mm-hmm. Thanks, Nangwan. Yeah. So as we've already seen, this AHU unit consists of several other components inside. So to model especially the filters, what we did is like we created a volume in the geometry. We didn't actually model the filter, as my colleague Nagman mentioned in the lower example. So instead of putting on the geometry details, you can model that as a simple volume and then go to the advanced concept where you have something called a porous media. So here you can define what is the pressure drop across this particular volume, and then you can set the flow direction. So you can even go for a higher level input of giving the pressure loss curve as a table input. So here you can give a series of points with response to the flow rate through the volume that you are simulating. And then you can set this to the simulation, and this way you can be efficient in the early stage design. And if you're really focused on validating a simulation or a product, then you can even bring in the geometrical details and simulate them. I hope that answered your question.
Thank you, Ajit. A related question to that was, what features does SimScale have for, altering, fixing geometry? Great time to mention some new features, including CAD mode, Ajit. Perhaps you can give a quick overview of that.
Mm-hmm. Sure. So within SimScale, you have certain options to modify the CAD. So although it's basically, it might be helpful if you want to make some quick design changes and then bring it back and simulate them. So what I did is basically took the original geometry. I came into the edit in CAD mode, which is a new feature which is attached to the SimScale. So here you can do certain options like deleting a face or extruding a face by moving, deleting a body, or doing a simple Boolean operations from here, and also rotate or transform the geometry. So these are some of the options that you can use to modify your geometry. Sometimes it's helpful in cleaning your geometry also. So if your geometry is quite dirty while importing, you can also use fixed interferences. This is really powerful, where it detects the overlapping geometries and fixes automatically. So these are some of the geometry editing options that you can use within SimScale.
Thank you. Thank you, Ajit. We have a really interesting question here about fans. On how do you model the performance of fans? For example, I saw a momentum source. So general question about modeling the performance of fans.
Sure, that's an interesting question. So there are certain approaches that we can actually handle to model fans. One simplest approach is actually putting a momentum source. For example, we have this blower. We didn't want to go into details of the fan because we're not interested in the performance of the fan itself. So we modeled that as a momentum source. So here you can see we're given a cubical volume here and then gave a particular velocity for the fan to operate with. So this is one of the approach that you can use. And a complex approach is actually to bring in the geometry of the fan itself. There you can actually make a rotating zone instead of the momentum source. And then here you can actually put the rotational velocity of the fan and also the axis of rotation. So this way you really model the fan itself within the simulation. So these are some of the approaches that you can use for fan modeling.
Great, thank you, Ajit. Let's take a couple more questions. An attendee is asking about how much control do you have over the mesh settings? And in the same question, can you define your own materials and material properties?
Sure. I'll go with the materials first. It's quite simple. So within SimScale, you do have a variety of material database that you can choose from. Although if you need a custom material needs to be analyzed in the simulation, you can simply select one of the default materials, for example, and then start modifying the material properties or the name of this material. So you modify the viscosity, density, or any other parameters that you want to modify, and then save that and apply to the simulation. This way you can use your custom materials for your project. And coming on to the second part, about the meshing. So as I already mentioned, we did a lot of investment in actually getting the requirements from our users and the kind of meshes they are happy with, and also convince the simulation or convergence itself. So you can simply use the default mesh settings. And if you're really specific, if you want to refine a particular region that's going to be affected by the flow, then you do have the options to create additional refinements, just like any other meshing tool. So you have the region refinement, where you can select a particular region and then say, I want this region at particular edge length. You can do that, or you can actually do a surface refinement, select a particular surface, give the maximum edge length to make sure we have the refined zone there. This also goes for the boundary layer refinement. We do have automatic boundary layer, but you can also set your custom boundary layer refinement if you are really specific about it.
Great, thank you, Ajit. Let's take one final question, again related to CAD modifications. So Ajit, we showed an example earlier, the ventilation louvers, where we had modeled that. That was actually a smart louver system from one of our customers. And we have an attendee asking if you wanted to model that same louver, but try and optimize the angle of the blades, right? So let's say you had 3 blade angles. How easy is it to modify those blade angles or geometry in SimScale and run, let's say, a comparison between 3 blade angles? What would be the kind of workflow to get that done?
That's again an interesting question. So if you have your blade angles modeled in initial geometry, what you can do is go to edit in CAD mode, and then you do have this translate or rotate option, where if your blade is modeled separately as a volume, you can select those volumes and then change the angle of the blade, bring a modified CAD, and then when you have the modified CAD, it's going to be simple to set up the simulation because you already have a simulation which is working, which you're confident with. you can simply duplicate this setup. So you'll get an exact copy of what you have set with the materials, with the boundary conditions, and also the mesh settings. You swap the geometry and then start the simulation again. This way, it just takes like 2 or 3 clicks before you start like 3 different geometry in parallel for your simulation.
Great, fantastic. So you could set up to begin with, 3, 4 different scenarios and simulate all of them in parallel. Thank you, Ajit. That's been really great. Okay, I think we will stop with the question answer session there. And thank you so much, Ajit, for presenting and the live demonstration you did. I'm just going to show people how to get started with SimScale. So it's time to roll up your sleeves. If you found what we showed you interesting and you want to have a go and discuss your projects or a more detailed one-to-one demo, please get in touch with us through the website, simscale.com, or you can contact us through sales@simscale.com as well. And we will also send a recording of this webinar to you in a day or two, and we will also include some links on getting started with the demonstration cases you've seen here today, including this air handling unit 1. Thank you so much for joining. I hope you enjoyed the webinar and have a good day. Thank you. Goodbye.
Thanks, everyone. See you in the next webinar.